May 1942, Aberdeen Proving Ground, Maryland. The morning sky hangs gray over the sprawling military complex where the fate of thousands of American infantrymen is about to be decided by a single test, a weapon so crude that senior Army officers are openly mocking it before a single shot is fired. The problem facing the United States Army was catastrophic in its simplicity. German tanks, particularly the heavily armored Panzer III, were rolling through North Africa and Sicily with near impunity. Standard infantry weapons couldn't penetrate their steel hulls. Grenades couldn't reach them. Rifle fire was useless. American soldiers had no practical way to stop an advancing tank, and they knew it. The casualty rates told the story. From November 1942 through May 1943, American infantry units in North Africa reported mounting tank losses with absolutely no effective counter. Officers couldn't find a single soldier in the theater who'd successfully stopped a German tank with any portable weapon. Not one. The War Department was desperate. Someone needed to invent a portable shoulder-fired weapon that could deliver a shaped charge warhead with enough force to penetrate armor. But this wasn't just any technical problem. It was impossible according to conventional military wisdom. The best weapons experts in the nation had tried spigot mortars, rifle grenades, and improvised contraptions. All had failed. All of them. What he didn't know, and what nobody else in that proving ground knew, was that standing in that Maryland test range that morning were two obscure Army officers. One of them just a first lieutenant with an engineering degree from Lehigh University, holding something that looked like a metal pipe with a rifle stock attached to it. Its sights were fabricated from a coat hanger and bent with a broken nail. The ammunition was a rocket that had already proven unreliable in previous tests. Military officials had already rejected rocket-based anti-tank concepts as unworkable. The competing designs were spigot mortars, actual proven technology that every expert said would win. But someone had to test this thing anyway just to complete the trial. What happened next would change warfare forever. But first, everyone in that test range would have to witness something they thought was impossible. A half-inch tube launching a rocket with no recoil, sights made from garbage, a weapon so crude it looked like something a private might fabricate in an improvised workshop instead of something the Army would ever field. This is the story of Lieutenant Edward Uhl and the weapon that was mocked, rejected, nearly canceled, and ultimately produced 476,000 times. To understand why Edward Uhl's invention was so desperately needed, we have to rewind to early 1942, when the Army faced a crisis with no solution on the horizon. The shaped charge technology existed. In 1941, Army engineers had developed the M10 anti-tank grenade, a shaped charge warhead capable of defeating up to 60 millimeters of vehicle armor, enough to stop most German tanks of the era. The problem was physical reality. The M10 weighed 3.5 pounds. It was too heavy to throw by hand. A soldier couldn't generate enough force to hurl it accurately, and infantry couldn't expect hand-thrown grenades to stop advancing armor reliably anyway. What good was a weapon that required soldiers to sprint toward a tank and somehow place an explosive charge directly on its hull? The casualty rate would be astronomical. Soldiers throwing grenades at tanks became dead soldiers. The Army tried everything else first. They developed rifle grenades, smaller shaped charge projectiles that could be launched from the end of an M1 Garand rifle. But these were weak, unreliable, and required riflemen to get dangerously close anyway. The effective range was pathetic. They couldn't be trusted to actually stop armor. After North Africa, senior officers reported that they'd never seen a single rifle grenade successfully disable a German tank in combat. Not one. They considered spigot mortars, weapons that fired projectiles using a spring-loaded mechanism. At Aberdeen, 5 different spigot mortar designs were being tested. These were the consensus picks of military experts. These were the weapons that board after board of ordnance officers believed represented the future of infantry anti-tank warfare. Spigot mortars had a long development history. They were understood. They were backed by established military theory. When the Aberdeen trial was scheduled, every expert knew which weapons would win. The spigot mortars, obviously. But there was a fundamental problem nobody could solve. No weapon the Army had tested could actually hit a moving target. The trial would include moving tanks, and every test weapon would need to score direct hits to prove effectiveness. The spigot mortars had already failed repeatedly in tests. They simply couldn't track moving vehicles. The accuracy was abysmal. Yet somehow these 5 designs were still considered the leading candidates, the safe bets, the consensus choice. The military establishment had invested intellectual and developmental capital into spigot mortars, and the military establishment protects its established investments. Meanwhile, back in 1918, a physicist named Robert Goddard had experimented with tube-fired rockets for the Army during World War I. He'd successfully demonstrated a rocket concept in November 1918, just days before the armistice. But the Army had lost interest after the war ended. Development stopped. Goddard moved on to other rocket research and eventually became legendary in the history of rocketry and space exploration. His early military rocket work was essentially forgotten. In 1940, when the Army finally resurrected the idea of a rocket-based anti-tank weapon, nobody was thinking about Goddard. Instead, the Army assigned Colonel Leslie Skinner to oversee a new development effort. Skinner's team would need to create a reliable tube launcher and a shaped charge rocket warhead that could work together. Nothing like this had ever been successfully fielded in combat. All the theoretical work existed, but the practical problems were immense. Rocket motors had to be reliable, shaped charge physics had to work at the precise instant of impact, and soldiers had to be able to aim and fire the weapon accurately while standing and holding it. The experts were extremely skeptical. Every military board that reviewed the rocket concept raised the same objections. Unproven technology, too many variables, unreliable ignition systems, inadequate sights, unproven in actual combat. The consensus was unmistakable. Focus on the proven technology, spigot mortars. Everyone agreed. What they didn't know was that by May 1942, one young engineer was about to prove all of them wrong. Edward Ohl was not supposed to be a weapons designer. He was a 24-year-old first lieutenant in the Army Ordnance Corps, assigned to Aberdeen Proving Ground with an engineering degree from Lehigh University and practically no combat experience. He had no background in weapons development. He'd never designed anything for the military. He wasn't the famous physicist or the senior general or the celebrated ordnance officer. He was a junior lieutenant with a college degree and a job nobody considered particularly important. His assignment was straightforward but seemingly impossible. Work with Colonel Leslie Skinner to develop a practical delivery system for shaped charge anti-tank warheads. That's it. No budget constraints mentioned. No timeline pressure explicitly stated. Just make this work somehow. Most junior officers would have recognized this as a subordinate engineering task. Design something, write up the specifications, and move on. Ohl saw it differently. He understood shaped charge physics. He understood rocket propulsion. He understood that both technologies actually existed and had been demonstrated before, separately. The question wasn't whether these technologies could work. The question was whether they could work together in a form that an exhausted infantryman could actually carry into combat and fire effectively while being shot at. The moment of insight came when Ohl was literally walking past a scrap pile at Aberdeen Proving Ground. Later, he would describe it simply, "I was walking by this scrap pile, and there was a tube that happened to be the same size as the grenade that we were turning into a rocket. I said, "That's the answer. Put the tube on a soldier's shoulder with the rocket inside, and away it goes." That was it. The entire concept in one observation. The shaped charge warhead was already built. The rocket motor existed. All he needed was a metal tube, literally something lying in a scrap pile, to contain the rocket and position it against a soldier's shoulder. The exhaust would shoot backward, but the key realization was that the backblast wouldn't actually require protective equipment for the operator. It would just vent behind him. Simple physics, obvious once someone figured it out. But somehow nobody had figured it out in this specific configuration before. Uhl began building a prototype. He worked with Skinner and another engineer named Clarence Hickman, who had continued Goddard's rocket work from World War I. Hickman was the intellectual descendant of Robert Goddard's original vision. Between the three of them, Uhl, Skinner, and Hickman, they had all the knowledge they needed. What they didn't have was time or institutional support. At the launcher's first firing test at Aberdeen, Uhl actually wore a welding helmet, expecting the backblast to be dangerous. After the first successful shot, he realized the helmet was unnecessary. The rocket's exhaust dispersed naturally. This wasn't a weapon that required complicated protective measures. It was simple. It was elegant. It might actually work. Skinner and Uhl realized they had something significant, but they also knew that nobody at the highest levels of Army ordnance was going to take a junior officer and his prototype seriously, not when 5 established spigot mortar designs were already in the testing pipeline, not when every military expert was backing the consensus view, and certainly not when the prototype was so crude that its sights had to be fabricated from materials borrowed from the scrap pile. But the trial was scheduled for May 1942. They had one shot to prove it. The Aberdeen Proving Ground trial in May 1942 would be the definitive weapons test. But Uhl and Skinner knew they were going in at a disadvantage. The 5 spigot mortar designs were the consensus choice. Military doctrine, established wisdom, official policy, everything was aligned against the rocket launcher. Senior officers had already invested credibility in the spigot mortar concept. Changing course now would mean admitting that the established experts had backed the wrong horse. That doesn't happen in military bureaucracy without extraordinary evidence. Uhl and Skinner worked in what might charitably be called a shop at Aberdeen, basically a workshop where they fabricated components, tested designs, and refined the launcher. There was nothing secret about it, but there was something isolating about it. They weren't part of the main development effort. They weren't receiving top-level briefings about the trial. They were just 2 officers working on a prototype that almost nobody believed in. The prototype launcher they'd built was 49 inches long and weighed 6 pounds. It looked exactly like what it was, a metal pipe with a stock attached and some crude sights. When Skinner and Uhl realized the night before the trial that the launcher had no proper aiming system, they improvised. They took a wire coat hanger, literally garbage, and bent it using a broken nail. That was their sight system. A coat hanger, a nail, nothing more. When military officers saw those sights the next morning, several openly laughed. "That's illegal," one colonel reportedly muttered. "You can't test a weapon with sights made from a coat hanger." But the rules of the trial were clear. Each weapon would attempt to hit a moving target tank. The tank would be moving. The gunners would have one chance to demonstrate accuracy. The 5 spigot mortar designs went first. One by one, the established designs attempted to track the moving target. One by one, they missed. None of the 5 mortar rounds hit the moving tank. 0 for 5. 5 military design programs, 5 teams of ordnance experts, 5 weapons backed by institutional consensus, and they couldn't hit a moving target. Then it was Uhl's turn. The bazooka, though it didn't have a name yet, was loaded with a rocket round. Uhl aimed using his coat-hanger sights. He fired. The shaped charge rocket ignited, traveled downrange, and struck the moving tank directly. Direct hit. One shot, one target acquired. Then they fired again. Another hit. The rocket wasn't just hitting the target, it was penetrating the armor. The test was over before it really began. When the demonstration was complete, General Gladian M. Barnes, the Chief of Research and Engineering in the Ordnance Department, walked over to examine the weapon. Barnes had watched all 5 spigot mortar failures. He'd watched the impossible success of the coat-hanger-sighted rocket launcher. According to witnesses, Barnes picked up the weapon, felt its crude construction, examined the improvised sights, and made a comment that would echo through military history. "That sure looks like Bob Burns's bazooka," Barnes said, referring to a 1930s comedian who played an actual musical instrument with a similar vague resemblance. The name stuck instantly. The M1 rocket launcher was now officially the bazooka, but nothing was approved yet. What happened next should never have happened, but it did. Despite the overwhelming evidence of the trial, 5 failures, 1 success, the military establishment did not immediately embrace the bazooka. The spigot mortar advocates were powerful. They had invested years in their designs. They had documentation, testing histories, institutional support. The bazooka was new, unproven, and backed by junior officers with a coat-hanger sight. The debate that followed the Aberdeen trial was intense. Ordnance officers split into factions. Some argued that the single successful test proved nothing. One trial doesn't establish a pattern. What if the bazooka failed in subsequent tests? What if battlefield conditions proved different from test conditions? The standard argument against any new weapon: we need more data, we need more trials, we need to be cautious. But General George C. Marshall, the Chief of Staff of the United States Army, had been informed about the trial results. Marshall was the man making the ultimate decisions about weapons procurement, military doctrine, and resource allocation. When he reviewed the data from Aberdeen, 5 spigot mortar failures versus 1 bazooka success, Marshall made a decision that bypassed all the bureaucratic caution. Marshall ordered 5,000 units of the M1 Bazooka immediately. The room erupted. Senior officers who had supported the spigot mortar program objected vehemently. 5,000 weapons was an enormous production commitment. This was money, manufacturing capacity, supply chain resources. The military establishment was built on careful deliberation, consensus development, institutional inertia. Marshall's order violated all of these principles. He wasn't ordering a limited trial production run. He wasn't asking for further testing. He was ordering 5,000 bazookas, full production commitment, based on the Aberdeen trial results. The opposition from spigot mortar advocates was fierce, but Marshall had the authority, and more importantly, Marshall had seen the data. 1 weapon hit a moving tank. 5 didn't. The mathematics were simple. The choice was obvious. Marshall ended the debate by placing the order. That decision, one general overruling bureaucratic consensus, changed the entire trajectory of the war. It also saved countless lives, though nobody knew that yet. Production began immediately. General Electric received the manufacturing contract and built the first 5,000 units in a crash program that summer. The bazooka was rushed into service by July 1942. Young soldiers received minimal training, often just a quick demonstration of how to load and fire. Many units had no formal training at all. The weapon was so new, the support infrastructure so underdeveloped, that soldiers were literally learning by doing. By September 1942, the first bazookas reached combat units. 600 M1 bazookas were shipped to Egypt for the British Army's use in the Western Desert Campaign against German forces. The British conducted a demonstration showing that the bazooka could penetrate the frontal armor of a captured Panzer III tank. The test was successful, but in the field things didn't go as planned. The M6 rocket ammunition proved notoriously unreliable in combat conditions. The battery-operated firing circuit wasn't robust enough for field conditions. Soldiers found that the rockets wouldn't fire consistently. Even when rockets detonated, they didn't always stop tanks reliably. The early bazookas in North Africa became sources of frustration rather than triumph. By May 1943, after the North African campaign ended with mixed results, the Army suspended further distribution of the bazooka. Senior ordnance officers who had opposed Marshall's decision felt vindicated. "See," they said, "we told you this weapon was unreliable. This is why we should have stuck with proven technology." But Uhl and Skinner weren't finished. They knew the fundamental concept was sound. They knew the failures were fixable. The rocket ignition system could be improved. The ammunition could be redesigned. The launcher itself could be refined. What was needed was systematic development based on combat feedback, not abandonment. By late 1942, the improved rocket launcher M1 was introduced. The design was simplified. Battery reliability was improved. The ammunition was upgraded to the M6A1 standard. These weren't revolutionary changes, but they were essential refinements based on actual combat experience. The second phase of the bazooka's story was about to begin. During 1943, as the improved M1A1 bazooka underwent testing with refined ammunition, the political and military landscape was shifting. The North African campaign had ended with German forces retreating from Africa entirely. The Allies were now planning Operation Husky, the invasion of Sicily, set for July 1943. This would be the first major island invasion in the Pacific and European theaters. American and British forces would land on a heavily fortified island, defended by German and Italian forces, with tanks, anti-tank guns, fortified positions, and prepared defensive lines. The question facing General Dwight D. Eisenhower was elementary. What anti-tank weapons would his invasion force have available? The spigot mortars had failed to deliver significant combat capability. The bazooka, despite its setbacks in North Africa, was still the most promising portable anti-tank weapon the Army had. Marshall's initial order for 5,000 units had been built. Eisenhower made a decision. The improved M1A1 bazooka would be issued to assault forces during the Sicily invasion. The testing data from Aberdeen in May 1942 had demonstrated penetration capability. The refined M1A1 design had improved reliability. The ammunition had been upgraded. The operators would receive more training this time. By July 1943, when Operation Husky commenced, American and British troops carried approximately 1,947 bazookas across the beaches of Sicily. The Sicily campaign from July to August 1943 provided the critical test. Small numbers of the M1A1 bazooka saw combat action against German armor. The statistical results were significant. The bazooka accounted for 4 medium German tanks and, most improbably, 1 Tiger Wash heavy tank that was knocked out when a bazooka round penetrated through the driver's vision slot in a shot of remarkable luck and skill. For the first time in actual combat, the bazooka had demonstrated that it could stop German armor, but more importantly, the Sicily campaign proved the concept. The fundamental technology worked. When aimed correctly and when hitting vulnerable points, the shaped charge rocket would penetrate armor that other infantry weapons couldn't touch. Word spread through the Army. The bazooka is effective. The weapon isn't just experimental anymore, it actually works. By September 1943, the Army began systematic distribution of the improved M1A1 to all divisions. A military division in July 1943 was authorized to have 557 bazookas assigned to its units. Smaller airborne divisions received proportionally more bazookas, since their soldiers couldn't rely on supporting armor or heavy weapons to the same degree as regular infantry. Every rifle company would have dedicated bazooka teams, typically 2 operators per company, carrying a single launcher and multiple rockets. The training standardized. Operators learned the effective range, approximately 300 yards maximum, but ideally closer to 100 yards for reliable hits. Soldiers memorized the ballistic calculations. Ammunition handlers learned the proper storage procedures. Maintenance teams developed protocols for keeping the weapon functional in various climates. Then came North Africa and the Pacific Campaign data that validated everything. By the end of 1943, statistics began accumulating. The bazooka demonstrated 78% reliability rate in tropical climate environments, a substantial improvement from the 34% failure rate of the original M6 rocket. The penetration statistics were consistent. The M6A1 rocket could penetrate approximately 89 to 102 millimeters of armor plate at ranges up to 300 yards. That was sufficient to defeat the side and rear armor of almost every German and Japanese tank in existence. Against frontal armor on heavily armored tanks like the Panther and Tiger, the bazooka was less effective. But infantry rarely attacked frontal armor anyway. They attacked from the sides, attacked immobilized targets, attacked when armor was exposed at vulnerable angles. By 1944, the statistics showed that 13% of German tank and armored vehicle losses in European combat were attributable to bazookas. That was remarkable for an infantry portable weapon competing against anti-tank guns, artillery, and tank versus tank combat. In 1944, the M9 Bazooka was introduced, a further refined design with improved accuracy, better reliability, and refined ammunition. The M9 was followed by the M9A1 in 1944, essentially the definitive World War II bazooka variant that would see the most extensive service. The M9A1 would become the most produced variant, 207,119 manufactured, coupled with the earlier M1, 112,790 units, M1A1, 59,032 units, and M9, 6,011 units. The total World War II bazooka production reached approximately 456,628 units. That's nearly 500,000 individual weapons manufactured. By comparison, General Electric and other contractors produced approximately 15,603,000 rockets for these launchers. Think about that number. 15 million individual rocket rounds, all manufactured during World War II to supply bazooka teams across every theater of operation. In January 1945, American forces captured a German Panzerschreck, the German copy of the bazooka that used an 80mm warhead instead of the American 60mm. When American officers examined the Panzerschreck, they recognized it immediately as a direct copy of the bazooka design that the Germans had captured in North Africa in 1942. The Germans had simply reverse-engineered it and scaled it up. That was the ultimate validation. The enemy itself acknowledged that the bazooka was the superior design by copying it. Then came February 1945, and everything changed. American forces reached the island of Iwo Jima. The Battle of Iwo Jima began on February 19, 1945. The volcanic island of Iwo Jima was fortified with approximately 22,000 Japanese troops, dug into bunkers, tunnels, and fortified defensive positions. The Japanese had constructed a network of underground tunnels stretching over 11 kilometers. Bunkers were reinforced concrete structures often covered with earth and camouflaged. Machine gun nests were positioned in overlapping fields of fire. Anti-tank guns commanded the beaches and approaches. The Japanese commander, Lieutenant General Tadamichi Kuribayashi, had prepared the island to be nearly impregnable. American forces would need portable anti-tank weapons that could destroy Japanese bunkers and fortified positions. The bazooka was ideal for this mission. While designed primarily as an anti-tank weapon, the shaped charge rocket was devastatingly effective against concrete bunkers and fortified positions. The M1 Bazooka could punch through solid concrete. At close range, a direct hit on a bunker would disable it, kill the occupants, or force abandonment. During the first 3 days of fighting on Iwo Jima, February 19, 1945, Marine and Army units using M1 bazookas destroyed 34 Japanese fortified bunker positions, 34 bunkers, in 3 days. The bazooka proved absolutely decisive in clearing fortified positions that would have required hours of assault or heavy weapons support otherwise. The casualty rate during those 3 days was catastrophic on both sides, but the American forces would not have succeeded in penetrating the Japanese defensive lines without the bazooka's devastating anti-bunker capability. The weapon that had been mocked as a tin can rocket launcher was now proven absolutely essential to assault operations against fortified enemy positions. The battle continued for 36 days total. American casualties reached 28,000 total, the highest casualty rate of any Pacific Island campaign relative to the number of troops committed. Of 22,000 Japanese defenders, only 216 surrendered. The rest died in combat or committed suicide rather than surrender. The island was devastated, the fighting was brutal, and American forces paid an enormous price. But without the bazooka, the price would have been infinitely higher. Edward Ohl never sought fame. He returned to civilian life after the war, eventually becoming president of Fairchild Industries Aerospace Company, where he directed the development of the A-10 Thunderbolt II aircraft, the famous Warthog that would prove decisive in the Gulf War decades later. When he died on May 9, 2010, at age 92, his obituary in the New York Times noted that he helped invent the bazooka. That was his historical legacy, boiled down to a single line. The bazooka itself survived long after World War II. It evolved into the M20 Super Bazooka in the Korean War, then into various other designs and derivatives used by every major military force in the world. The fundamental concept, a soldier portable shaped charge rocket launcher, became the foundation for modern man-portable anti-tank weapons like the Javelin and countless others still in service today. Today, more than 80 years after Aberdeen Proving Ground, the fundamental technology is still used. Modern RPGs and shoulder-fired anti-tank missiles operate on the identical principle that Edward Ohl understood when he picked up that metal tube from a scrap pile. The shaped charge warhead, the rocket motor, the recoilless launch system. These are the same technologies deployed across the world by military forces today, all because one young engineer understood something simple. Sometimes the best solutions are the simplest ones, and sometimes the establishment is wrong.